Okay, thank you very much. Thank you very much for the introduction. Good evening from Japan. I would also like to thank all of you for giving me an opportunity to present our recent work online. As Sergey mentioned, I'm a senior advisor of Riken Center for Emergent Matter Science near Tokyo. At the same time, I'm a visiting chair professor of the Kavli Institute for Theoretical Sciences in Beijing. But because of the COVID-19, I have not been to Beijing for 3 years. And also the third address is my former institute, Advanced Science Research Center, of which I was the director. So in this talk, I'd like to present the hydrodynamic effect in electron fluids on spintronics. As I'll show in a minute, this is a new paradigm in electronics and spintronics. This work has been done in collaboration with many of my colleagues, especially my young co-workers in theory, Matsuo at KITS, Kavli Institute, Fujimoto at Saitama University, Yamamoto at the Advanced Science Research Center, and Koshibai at Riken. The co-workers in experiment will be presented together with their data during my talk. The introduction of my talk is given in, sorry, it's strange. It doesn't move. Sorry. Given in this textbook entitled Spin Current, published from Oxford University Press, especially the chapter 25 is entitled the Spin Mechatronics. This is my introduction part. Okay, the upper figure shows the charge current where up and down spin electrons flow in the same way. But on the other hand, the bottom figure shows the spin current where up and down spin electrons flow in a different way. Therefore, the charge part is cancelled and we have just the flow of spins. This is spin current. The charge current and spin current can be interconverted easily by using the so-called spin Hall effect. As in the left figure, we introduced charge current from the left, and then the electrons are scattered by spin orbit scatterer. Then we have the spin current in the perpendicular directions. Because of the spin orbit scatterer, the electrons are scattered a different way, depending on spins. This is called the spin Hall effect. On the other hand, in the right, we introduce spin current. Then electrons are scattered by the spin orbit scatterers, and we have this charge current. This is the inverse spin Hall effect. In this way, a spin current and charge current are interconverted quite easily. Therefore, we manipulate the spin current, and then if necessary, we convert the spin current to charge current, and we measure the information and something. This is the spintronics. Okay, so now let me ask, what is electron hydrodynamics? And second, how do we get electron hydrodynamics? And third, why is electron hydrodynamics interesting and important? Let me answer to the first question. In the usual metals and semiconductors, electrons are diffusive. As shown in this figure, the flow of electrons are smooth. On the other hand, the flow of water and the flow of liquid metals are different, as shown in the bottom figure. They are sticky. So these are the hydrodynamic flows. So question is, what gives rise to the difference between this diffusive flow and hydrodynamic flow. In the hydrodynamic flow, electrons are mostly scattered by the impurities. Therefore, the electron-electron scattering is not important. In this case, we have the hydrodynamic flow, and the flows follow the diffusive equation. On the other hand, if the impurity scattering system is very clean and the impurity scatterings are neglected, then electron-electron interaction becomes important, where the electron momentum is conserved during the scattering. In this case, we have the sticky flow. This is the hydrodynamic flow of electrons, and the flows follow the Navier-Stokes equations. And the important concept in the hydrodynamic flow are viscosity and vorticity. In the diffusive flow, we do not have viscosity and vorticity. Therefore, in the hydrodynamic flow, viscosity and vorticity are the key concept. So the hydrodynamic flow of electrons, a new paradigm of electrons, electronics and spintronics, and such systems has been obtained based on the technology of 21st century. In that sense, hydrodynamic flow of electrons are a new paradigm of electronics and spintronics. Okay, this is the content of my presentations. First, I'll discuss the hydrodynamic flow of liquid metals. And then we extend this idea to the electron systems. And the second part, I'll introduce the graded materials. And the third, I'll discuss the magnetic skyrmion generation and annihilation by electric current. And green, the differences are shown in the green color here. Okay, let me start from some introduction. You remember the Foucault pendulum. Because we are on the rotating Earth, therefore the pendulum behaves in this way. This is because of the Coriolis force due to the rotating Earth. Here, the angular momentum, total angular momentum between the Earth and the pendulum are conserved. Therefore, we have this Hamiltonian. Here, L is the angular momentum of the pendulum, and omega is the rotating frequency of the Earth. If this pendulum has spin, we have the total angular momentum conservation between the Earth and the pendulum. Therefore, we have the second term as well. This is the spin rotation coupling. So this interaction is very important. In 1915, Einstein and his co-workers studied this rotation effect on magnetic materials. They rotated an iron rod. I'm sorry, they applied the external magnetic field on the iron rod. Then this iron rod is magnetized. At the same time, this iron rotated. In the same year, Barnett rotated the iron rod, and then he found that the iron rod is magnetized due to the rotation. Therefore, he found that rotation works as an effective magnetic field. So this rotation is called Barnett field. In this way, these people showed that the rotation and the magnetism is the same. And later it was shown that these effects are described in this Hamiltonian spin rotation coupling. Although at that time in 1915, this was before the discovery of quantum mechanics. So therefore, people, including Einstein, did not know the existence of spin. Okay. So now we can consider that electron is a microscopic rotor, namely the upspin is right rotating rotor, and the downspin electron is a left rotating rotor. In this way, we can consider the electrons and the interaction between electrons and rotations. Now, if we first consider the liquid metal, say mercury, the flow is something like that. So when we look at the flow inside in detail, flow is, we have the local rotation of the fluid in this way. So this rotation is also spatially dependent in that way. So we remember the Stern-Gerlach effect, namely, when the magnetic field is spatially dependent, then the gradient of the magnetic field acts on spin as a force. In the same way, rotation spatially dependent. Therefore, the gradient of the rotation acts on a spin as the Stern-Gerlach force. So we have the spin current in this way, flow in this way. The spin current flow this way. Once we have the spin current is converted to the charge current in the flow direction because of the spin Hall effect. In this way, we have the spin vorticity coupling, because vorticity is the rotation of the spin following this Hamiltonian. So we can consider the following thought experiment. We introduce the spin current in a liquid metal, then the spin current, angular momentum of spin current is converted to the rotation of the fluid. So we have the vortex of a fluid. In the inverse situation, if we have a vortex of a liquid metal, then this rotation is converted to spin current, and spin current is created. This thought experiment was realized in this way. We consider first the mercury flow in the cold tube. We apply the pressure here, and the mercury flows in this way. And we put the voltage terminal in this way. Then we find that during the flow, we get the voltage. This is we call spin hydrodynamic generation. So left-hand side shows the voltage as a function of the time. During the flow, we have the voltage here like this. When the flow direction is reversed, we have the opposite sign of the voltage in that way. The right-hand side, we change the pressure of on the flow. Therefore, we change the velocity of the flow. Then the velocity increases, then the voltage increases in that way. In this way, the mechanical motion can be converted to the electric voltage via the spin current. So this effect can be solved by introducing the fluid dynamics, spin dynamics, and the spin Hall effect. And in the turbulent flow case, we have this equation. Here, V star is the flow velocity. And so in this turbulent flow case, voltage, induced voltage here is proportional to the velocity square. So the spin current is mainly generated in the vicinity of the pipe wall. So we also studied the laminar flow case. Then we have found the laminar case, induced voltage is proportional to the flow velocity. This is different from the turbulent flow case. In this case, voltage is proportional to the flow velocity square. This is the experimental data shown here and here. So this is because in the turbulent flow case, vorticity exists only at the pipe edge. On the other hand, in the laminar flow, vorticity exists in the whole range of the flow. This is the difference. Recently, gallium indium tin. This is another liquid metal. Gallium indium tin has been studied by these two papers by the people in Germany, and together with the Russian Moscow people and New York people, university, and they found in gallium indium tin alloy liquid, they obtained the same kind of spin hydrodynamic generation. Here, the gallium indium tin has the melting point temperature to be 10.5 degrees C. You see, this left-hand side is gallium indium tin liquid. This is looks quite different from a mercury case, but in the case of spin hydrodynamic generation, they are quite similar. This slide shows their result in gallium indium tin. You see in the laminar flow, this is the voltage, induced voltage as a function of flow velocity. They find the linear relation in the laminar flow case. In turbulent flow case, they find that voltage is proportional to the flow velocity square in that way. This is consistent with the mercury case. This slide shows the efficiency of the hydrodynamic generation. Efficiency is defined by the electric energy, induced electric energy, divided by the flow energy. As a function of the Reynolds number, you see we have this tendency. So the efficiency is still very small, but this is the new kind of the energy generation, electric energy generation systems. So we are trying to increase this efficiency, and now it's getting better and better in that way. Okay, so when we published this result, the Nature Physics journal named this effect, namely the spin hydrodynamic generation, to be the fluid spintronics. So now it's called the fluid spintronics. So this is the case of liquid metal. So now, how about the hydrodynamic flow in electrons? This is the next subject. So as I mentioned, usually usual metals and semiconductors, electron flow is a diffuse flow. But in pure systems, we have the hydrodynamic flow of electrons shown in the left. So once we have the hydrodynamic flow of electrons, then we have a vorticity, the rotation of the velocity. So we have a vorticity, and then we have the spin vorticity coupling. This is the next subject. So in that case, the electron-electron interaction is the main scattering mechanism, and electron momentum is conserved during the scattering. Therefore, we have a hydrodynamic flow. Now we have several systems and materials which show the hydrodynamic flow of electrons. They are pure graphenes and the two-dimensional palladium cobalt oxide and tungsten phosphide and nanostructures, gallium arsenide. And it's interesting to see that these systems, how about the spin, fluid spintronics? This is the very interesting subject. But in this talk, I'll not touch in these materials, but maybe I'll say a few words about the graphene case. This is the theoretical result of the single-layer graphene's phase diagram as in space of temperature and chemical potential. Zero is the Dirac point. You see, as shown in the orange region, we have the hydrodynamic fluid which is sometimes called the Dirac liquid. And figure B is the behavior of the flow, of hydrodynamic flow. We introduce the electron current from this hole. Then the hydrodynamic flows, we have this kind of the rotation. And because of this backflow, we have the negative resistance. This is the experimental result in Manchester. Okay, so I will not touch the graphene and other hydrodynamic two-dimensional systems, but I like to introduce different systems, which is the graded materials. In the right-hand side, we show the graded materials where the composition is spatially graded, as shown in this way. And the graded material is quite popular in, for instance, the human bone is a graded materials. And also in the upper figure, space planes are covered by the graded ceramics materials, where the thermal conductivity is spatially graded. Now, we have studied the surface oxidized copper film as a spintronic materials. This is the schematic figure. In the left, we have the copper metal. Then this upper surface is oxidized. Then the oxygen concentration is spatially graded in this way. Therefore, when we introduce the current in the y direction, then because of the spin vorticity coupling, spin current is generated in the z direction. And when we put this graded material copper on top of permalloy, then this spin current interact with the magnetization of the permalloy. Therefore, as a result, the current depends on the magnetization. And this is called the unidirectional spin magnetoresistance. The right-hand side is shows the schematic figure of the mobility of electrons in the graded materials. You see, the copper oxide is the insulator, the mobility is 0, and the bottom part is the pure copper. And in between, we have the gradient of the mobility in this way. This is one of the experimental results obtained by the KO group. This is the y-axis shows the magnetoresistance due to the unidirectional spin magnetoresistance mechanism as a function of the current density. And the green circles are the graded material case. You see, we have the effect, but pure copper case shown by orange squares, there's no effect like this. In this case, in this way, we have the unidirectional spin hole magnetoresistance. And from this result, we can estimate the spin hole angle of the graded copper. Then this value is similar as the platinum case. So we can use this graded copper as a spintronic materials. So we also introduce the spin current into these graded materials. Namely, we introduce the microwaves, and then the precession induces the spin current, and spin current is injected into the graded copper. But we could not observe any voltage here. Namely, there's no inverse spin Hall effect. So we have a large spin Hall effect, but we did not obtain any inverse spin Hall effect in this graded materials. So we can say the graded materials is, has non-reciprocity and the spin current and charge current convergence. So in this way, this graded material is quite unique spintronic materials. So non-reciprocal spin current generation is seen in spin surface oxidized copper film. And now we are working together with Irina Pianzina at Kazan in the other graded materials and interfaces, in addition to the copper oxide, copper 3 nitrogen copper, and the silicon aluminum case, and also the metallic state at the oxide interfaces. So we see how interesting in these materials in a minute, later. Okay, now I move on to the next topic. That is the magnetic skyrmion generation annihilation by electric current. This is given in this paper. Left-hand side is the TM picture given by Riken, my institute. You see, by applying the magnetic field, we have the black dot. These are the skyrmions. And the right-hand side is the simulation result of the skyrmions. And the arrows denote the magnetization direction. The skyrmion is this side. So skyrmion is a quite small magnetic structure. Therefore, we expect that skyrmion can be used as the magnetic memory. Then the people are working the skyrmion very actively. This is the case of iron germanate. Okay, so figure A and B are the iron germanate film, and figure C is the magnetic phase diagram in the space of a magnetic field and temperature. The Curie temperature, transition temperature, iron germanate, it's around 270 Kelvin, and near the Curie temperature, we have the skyrmion phase shown here. Now, we introduce this notch. We cut this part like this in this film. And we introduce the current from the left to the right in this iron germanate film. Then we have the phase diagram shown by figure F. As you see here, there's a large skyrmion phase exists in the large regions. Interesting is that the skyrmion phase appears even without external magnetic field. Another more interesting is that when we change the current direction, this skyrmion phase disappears. So we find that the skyrmion generated at the corner of the notch, something here. The notch size is something like that. This is the 500 nanometer. So we summarize the experimental result given in Riken people in the bottom of this slide. First, the skyrmions are created at the edge in the positive plus current, and the current value is quite small compared with the spin transfer torque current. And the second, the skyrmions are annihilated in the minus current. The current direction is reversed, then skyrmion phase disappears. And the third is that the skyrmion creation and annihilation occurs even without magnetic field. So we know that at the edge, there exists the current vortex from the fluid mechanics, for instance, in the Landau's textbook. So we examine the current vortex near the notch edge in this way. So current flows and current go around the notch like this. Therefore, we have the vortex at the edge in here and here. And then we have found that due to the current vortex near the edge of the notch, there appears the effective Zeeman field due to the vorticity. And second, the Jelsinski-Moria interaction is induced due to the vorticity of the current. The upper figure shows the effective Zeeman field. When we introduce the current, then and this vortex of the current induces the effective magnetic field through the SD exchange reaction shown here, and something like that. And this effective field is proportional to the vorticity. And effective Jelsinski-Moria is induced via between the localized spins via the vorticity in this way. So I'll not go into the details, but effective Zeeman field due to the current vortex is proportional to the SD exchange interaction linear, and the effective Jelsinski-Moria interaction is given by the square of the SD exchange interaction. And I estimate the value of this effect. The Zeeman, the Zeeman effective Zeeman field is of the order of 0.1 Tesla, quite large, and the effective Jelsinski-Moria interaction induced by the current vortex is this 10 to minus 2 electron volt. This value is similar as the original Jelsinski-Moria interaction in the ion germanate. So we emphasize that the current vortex has also the induced the Ampere magnetic field, but this is very, very small, 10 to minus 5 Tesla. So this effective magnetic field is induced through the SD exchange interaction. So because of this effect, we have the current skyrmions near the edge. So I just show the numerical simulation. This is the notch of, and we introduce the current from the left to the right, and then magnetic structure is induced, and we have the skyrmion in this way. This is the simulation result. We also introduce some hole in the ion germanate and introduce the current from the left to the right. And we do the simulation of the velocity distribution of the current and electric field and vorticity. So we see in this way. Yeah, it's very small, slow, but you see, we have the so-called Kalman's vorticity. Kalman vortices due to this hole, current flow this way, and we have the current Kalman's vorticity in this way, like this, maybe like this. So in this way, we can design various nanostructure in the magnetic films, and we introduce various skyrmion structures this way. Okay, this way. Okay, so in conclusion, in nature, there are a variety of vortices, from the galaxy to typhoons to bathtub vortex and Abrix vortex of superconductors and quark matters. So we are interested in the hydrodynamic flow. Here, the vortices have angular momenta and coupled to the spins. Therefore, we have the various interesting phenomena called in fluid spintronics. But we hope in other systems, we have some kind of different interesting phenomena, which may be called the fluid dynamics. So in 217, high energy people in Brookhaven studied the Koch-gluon plasma. They did the following experiment. The off-center collision of gold-gold nuclei produces Koch-gluon plasmas with very high rotations, as shown here. At the same time, the spin polarized lambda hyperion was emitted this way. So in this paper, in Nature paper, they wrote in the beginning in the following way. Takahashi et al. This is Mercury's result. Takahashi et al. Reported the first observation of a coupling between the vorticity of a fluid and the internal quantum spin of the electron, opening the door to a new field of fluid spintronics. In a heavy ion collision, shear forces generated by the interpenetrating nuclei may present an analogous situation, introducing the vorticity to the fluid. In this way, high energy people watching the spintronics works, and now the high energy physics and spintronics go hand in hand. So in summary, hydrodynamic flow is a new paradigm in condensed matter physics. In particular, vorticity of fluid couples electron spins and provide a variety of spintronic properties. So in nature, there are various kinds of vortices. We like to study these vortices, and we hope that the spin current is everywhere in the nature.